calculus on parametric curves. So we know that dy dx can be expressed as dy dt over dx dt, which allows us to find tangent lines. Tangent lines are a pretty much fundamental concept with differential equations, with functions, but in parametric equations we should be able to find tangent lines as well. So let's start with a fairly simple idea. Let's take x is equal to t squared plus 3 and y is equal to the square root of t minus 8. We don't even have to know what this actually looks like. What we want to do is we want to find a tangent line. We know that dy dx talks about the slope in the rectilinear coordinate system of the tangent line. So if we calculate dx dt, which is 2t, calculate dy dt, we 1 over square root of t, and now we know that dy dx will be equal to 1 over 2 root t divided by 2t, which when we invert and multiply, we get 1 over 4 t root t. Now, this curve, some unknown curve, well, in order to find that unknown curve's tangent line, we just need to evaluate this at a point. Say t equals 4. Well, then we get 1 over 4 times 4 square root of 4, which is 1/32. So let's suppose that right here, let's suppose that right there is the point associated at t equals 4. Well, then the slope of this tangent line here can be used in the equation of y minus y naught equals 1/32 x minus x naught. And now to get the x naught y naught, you've got to go back to the original function and evaluate that. So x at 4 is 16 is 19, and y at 4 is negative 6, and so you'd have the point y minus 6 equals 1/32 x minus 19. Now, admittedly, 19 minus 6 is not what that point looks like. This is just some spoofy thing drawn, but this is how you can find a tangent line. Well, let's do polar. Now, if you remember when we did the chain rule on the polar equation, they look pretty nasty as to what that form looked like. So you either have to memorize that formula for the derivative in polar, or you have to choose to write it in a slightly different way. So the one equation that we did in polar that had the r sine theta, r cosine theta, and then we calculated all the derivatives, it actually can be simplified to the following rule. It is nothing more than sine theta over 1 minus cosine theta when it's all done. That's what is a result of the polar derivative in converted to rectilinear form. So where did that come from? That came from dy d theta over dx d theta and its subsequent simplification. So if I give you some equation, and so let's do a very standard equation. Let's do r equals 4 cosine theta. So that brings us all the way up to 4 like this. It goes around. Center is 2. That's the polar form generated over a cycle of theta from 0 up to pi. Whoops, didn't need to hit pi. I hit that point twice. So a couple of tangent points here, lines that should be absolutely obvious. We should be able to see this, that horizontal tangent lines happen at very specific angles. So let's first off observe that this angle should produce something nice. So dy dx associated with theta equals pi fourths will be the sine of pi fourths over 1 minus the cosine of pi fourths, and I have made a mistake. Let's do polar. So if you remember, we did the chain rule from polar as well, which was dy dx equals dy d theta over dx d theta. And since r cosine of theta was the x and y was r sine of theta, and if you remember r was a function of theta, we were able to simplify this down to dr d theta sine theta plus r cosine theta over dr d theta cosine theta minus r sine theta. So if we want to do tangent lines in polar, well, let's write down a fairly simple polar equation. Let's write down y equals 4 cosine of theta, which is a circle like this, out at 4, 0, here's 2, 0. That's in rectilinear. Turns out, let's do this point right here. Let's see if we get a tangent line of 0 at theta equals pi fourths. Well, in order to do this, we need to calculate some values. So dr d theta, derivative of cosine is minus sine, so we get minus 4 sine theta. So that's what we're going to put in here. So this, for this particular equation, will be minus 4 sine of theta squared plus 4 cosine squared of theta all over, well, at this point I actually can stop because I'm going to plug in pi fourths here, and I want you to know sine and cosine are equal to pi fourths. This will be 4 cosine squared minus sine squared. This is going to be a 0 at the top. We want to make sure the bottom's not 0, so we'll continue. Dr d theta again is minus 4 sine theta cosine theta minus, and then it'll be r, which will be 4 sine theta cosine theta. And this is a non-zero quantity. And so we get a slope of 0. So we now have a tangent line. And again, when you do the tangent line, you don't put the polar form in because this is rectilinear, so that you would put the x's in. And the x's are, of course, are determined by the relationship. First you find the polar form, then you do a Cartesian and you put it in. So it can be a multi-step process. Now, once we've done these tangent lines, then, of course, what we want to do is we want to ask ourselves about things like how long are pieces of parametric curves or polar curves? What area is encompassed inside of them? So all of the things that we did in rectilinear, we want to repeat in these different forms of equations. Now, it turns out that polar, the formulas are kind of funky. They're really based upon this idea. A equals 1/2 r squared theta. Now, that's an equation that you would ask yourself, where did that come from? And it's one of the fundamental reasons that we pick radians to do math, and it's also one of the fundamental reasons that the formula is going to end up looking the way it looks. So first off, I just want you to imagine that we have a circle, and we have a small arc of that circle. So here's a very small theta and radius. Okay? Now, obviously, this theta and small pizza slice is a proportion of the an entire circle. So if you want to calculate the circle you have, well, then you would take theta divided by 2 pi when theta's in radians, and this will be the proportion of your circle, times the area of circle you have, which is, well, in that pi r squared. So then when you cancel, why, lo and behold, that's the formula you get when you draw a very small pizza slice in radian measure. Now, if we take a very strange polar function, and we go out here, that's not really a circle, but if you take a very small angle in here, then that little pizza slice looks like the following. There's the function. Here's the arc of the pizza slice. Some might be a little bit above, some might be a little bit below, but in general, that pizza slice is going to be almost exactly the area of the piece of the function. So what kind of formula does this lead to? Well, it leads to the following simple way to remember this. The area in a polar form is nothing more than the integral of 1/2. Now r is your f of theta. You square it. And then your angle, though, needs to be a teeny slice, so that's the d theta. And of course, it starts from theta 1 and goes to theta 2. Well, that's a fairly simple way to calculate things. So, as an example, on that r equals 4 cosine of theta, let's suppose you just take theta equals pi sixths here, and theta equals 0, and you want to know how much of the circle do you have here. Now, that's not a circle centered at the origin, that's a circle centered here, so that's not really a very good pi shape. But you'll notice how clearly it does look like that. Well, the integral then is from 0 to pi sixths of 1/2 16 cosine squared theta d theta. And this is one of those nasty integrals that you have to calculate out and evaluate, but you can find this area. These applications are fairly straightforward. So, any good mathematician can make the problem harder, right? So, how can we make this harder? Well, some of these polar forms, r equals f of theta, get pretty wild. And when we talk about wild, they can do things like this. Big loop, big loop. I mean, they can be crazy. So if they can get crazy like that, then it becomes rather difficult to understand which specific area we're talking about. And what we say is we say the area swept out by theta 1 to theta 2. So let's suppose we have a figure. I'm going to make a simple figure that has some funk to it. Now, let's say I started at 0 and went to pi halves. Well, then the area being swept out is right there. And this little piece in there isn't relevant because it hasn't been created from theta to pi, theta equals 0 to theta to pi halves. So if you set up this integral to do the integral from 0 to pi halves of this function, 1/2 f of theta squared d theta, then the little loop hasn't been created in that space, and so you're getting all of this, which is somehow vastly different than how we see it in a rectilinear. So how do we make sure that we know what areas we're creating? Well, we need to know when things are being created in a process. So let's do one of these here. Let's create a function. I'm going off of page 670 here. We're going to do a looped four-leaf rows. We're going to do r equals the cosine of 2 theta. Now, I'm not going to use a calculator to draw it. I'm going to figure this out independent of a calculator. I'm first going to notice that cosine varies between -1 and 1, which means this picture is going to be bounded by the circle 1. It's inside of it. So that's the maximum value. Now, I also know that when cosine is 0, theta is 0, 2, 0 is 0, cosine of 0 is 1. I know here is a point in polar of r theta, which will be 1, 0. Now, let's move up to a slightly larger angle, say pi fourths. 2 times pi fourths is pi half, cosine of pi half is 0. So as I move this way, I've already come back to this point. It turns out this is what happens in this loop from 0 to pi halves. Well, kind of be nice to keep going and discover that it looks like this. And now you can ask yourself, how often do we come back to 0 to create this? So we want to go back to pre-calculus and we want to solve the cosine of 2 theta equals 0 and understand why is it that we were there once, twice, 3 times, 4 times to make this. And over what angles did that require us to make it? So if you think about it, it took 0 to pi fourths to get this. There seems to be 1, 2, 3, 4, 5, 6, 7, 8 of those half loops. It looks like we might take a whole 2 pi to go around. I'm not sure. Let's find out. So in solving this, the first thing I do is ignore the 2 theta and just simply graph cosine of x. And cosine of x starts at 1 and goes like this. I'm going to go this way as well. I'm going to observe then that where's a good cycle to look at? Well, there it looks like a bunch of zeros. All right, so let's observe here at minus pi halves, pi halves, 3 pi halves, and 5 pi halves that I found a bunch of zeros. But that was graphing cosine x. So x is really representing 2 theta, so the 2 theta when equal to minus pi halves, 3 pi halves, and 5 pi halves, all of those make cosine of that 0. So here's a list of angles that make this function, this radius, 0. So I see theta equal to minus pi fourths, pi fourths, 3 pi fourths, and 5 pi fourths, that this is going to be 0. So it looks like if I start at minus pi fourths, I'm here, and as I go around at 0 I reach there, and at pi fourths I'm back to here. So it seems that from minus pi fourths to pi fourths is when I create this loop. So when does this loop get created? Well, as we're going from pi fourths to pi halves, notice if theta is from pi fourths to pi halves, that's a quarter of a pi, that's a pi fourths, which is half of a leaf. Which one does it create? Well, double the angle. And now when you take the cosine of this, you're taking the cosine of angles between pi halves and pi, which are negative. So as you're going from here, from pi fourths to pi, you're plotting negative angles. So this arc swept out by theta from pi fourths to 2 pi halves creates this arc on the 4-leafed rows. So if we finish to here, that loop is created. So this loop is created from minus pi fourths to pi fourths, while this one is created from pi fourths to 3 pi fourths. So now we know how they are created, so we can set up any integral we like to do a leaf here. So one integral we can set up is the integral from minus pi fourths to pi fourths of 1/2 f of theta squared d theta. And again, this is a nasty integral. I would first check u equal to 2 theta and then remember or look up the integral of cosine squared. And you can get the area. What's surprising is we can also do this to get this leaf, and that leaf would be the integral from pi fourths to 3 pi fourths of 1/2 cosine squared of 2 theta d theta. And so one integral calculates this area, one integral calculates this area, and you find out they evaluate all to the same. Okay, so again, any good mathematician can make it harder. So now, let's suppose we have a figure like this. There's the origin. And let's suppose we want this area, but not that area. So what we have to do is we have to figure out the theta 1 to theta 2 that generates this piece of the arc. We then have to figure out the theta 3 to theta 4, which generates this piece of the arc. And this angles used in the integral will calculate this area, and this angle used in the integral will calculate that area, and when we take the difference of them, will be outside of this arc, but inside of that arc. So actually, finding the space between two curves in polar actually means that you frequently have to find more than one integral. What it used to be in rectilinear was simply we had an a to b where we took an f minus a g. Now, in polar, we may have to do a theta 1, theta 2, 1/2 f of theta squared d theta minus, and the other piece is generated in a different angles, so theta 3 to theta 4, 1/2 f of theta squared d theta. So there's an added complexity that exists in polar form. All right.